It seems like every day, AI is doing something more and more amazing, like composing music,
Right.
writing code, even holding conversations that are pretty darn convincing.
Yeah, it really is incredible.
But have you ever stopped to think about what's happening behind the scenes to make these systems so powerful?
It's really a fascinating area. There's a constant push to make AI not just smarter, but faster and more efficient as well.
Exactly. And that's what we're diving into today.
Yeah.
I've got this excerpt from a Google AI blog post
Oh, yeah.
that talks about how they are tackling this challenge, boosting AI performance.
Right.
Specifically, we're looking at large language models, LLMs,
Yeah.
which are like the brains behind a lot of the AI applications that we all use every day.
These LLMs are truly remarkable, but they need a tremendous amount of computing power. We're talking tens of exaflops.
Okay, so I have to admit, when I saw exaflops, I had to look it up. Do you want
Uh,
to try to explain that one to me and maybe help out anyone else who's wondering what in the world an exaflop is?
sure. So an exaflop represents a quintillion calculations per second. To give you some perspective, if you had a computer that could perform one calculation every second, it would take over 31 billion years to perform an exaflop of calculations.
31 billion years.
Yeah.
I think that qualifies as mind-boggling.
Yeah.
But here's the thing that really surprised me in the article. Making LLMs faster isn't just about having more powerful processors. A big part of it is about using memory in a more clever way. Almost like being a really, really organized librarian or something.
That's a great analogy. And you're right, it's a crucial aspect. See, a large chunk of an LLM's memory is dedicated to storing these things called weights.
Okay.
These weights are numerical values that determine how the model learns and makes decisions.
So the more weights an AI has, the smarter it is.
In a simplified way, you could think of it like that. These
Yeah.
weights are used in tons and tons of matrix multiplications, which are the fundamental mathematical operations behind how AI processes information.
Gotcha.
These multiplications are really memory intensive and take a lot of processing power.
So that's where this memory bottleneck comes in. It's like trying to cram all the books in the library onto a single shelf.
Right.
But the Google article mentioned something that sounds almost like a magic trick. Using smaller data types to store the weights.
Exactly. Instead of using the standard 32-bit numbers, which take up a lot of space, they found that using 8-bit integers can be just as effective for storing many of these weights.
Interesting. So what kind of impact does that have on memory usage?
So 8-bit integers, which are called U8 or S8,
Okay.
can reduce the memory footprint by a factor of 4 compared to the typical 32-bit representation F32.
Wow.
And they're also half the size of 16-bit numbers like F16 or BF16.
Okay, so that's a huge improvement.
Yeah.
Why isn't everyone doing this? It seems like a pretty obvious win.
Well, there are a few hurdles. One is that it requires using a technique called weight-only quantization.
All right, you've officially used a word. I need you to break down what exactly is weight-only quantization.
Sure. Essentially, it means you keep the user input in high precision, for example, using 16-bit numbers in the F16 format to maintain accuracy. But for the model's weights themselves, you can use those smaller 8-bit integers. Research has shown that this approach maintains accuracy while significantly boosting efficiency. It's a really clever trade-off.
So it's like getting the best of both worlds, accuracy and speed.
Mm-hmm.
But you said there were a few hurdles. What else is standing in the way of this becoming the standard approach?
Well, the other major challenge is the hardware itself. The hardware accelerators, like the GPUs that power most AI systems, often have limited support for these mixed input calculations, where you're combining 8-bit and 16-bit numbers.
So it's not as simple as just flipping a switch and saying, use smaller numbers.
Unfortunately not. To illustrate this problem, the Google AI blog post specifically focuses on the NVIDIA Ampere architecture, which is widely used for AI processing. NVIDIA GPUs have these specialized processors called tensor cores that are designed to handle matrix math very efficiently.
Okay, so they're like the super-powered math brains of the GPU world.
Exactly. But here's the catch. Tensor cores are very particular about the types of data they can work with and how that data is laid out in memory.
So even with this clever idea of using smaller data types, we run into another bottleneck with the hardware itself.
Precisely. And that's where Google's ingenuity comes into play. They've developed some really clever software tricks to overcome these hardware limitations.
That sounds like a good place to pause. We'll dive into those clever tricks in part 2 of our deep dive. All right, so we left off talking about how these tensor cores, those super-powered math brains inside NVIDIA GPUs, are really picky about the data they'll work with.
Right, they have very specific requirements.
Yeah.
And when you're trying to mix those smaller 8-bit numbers with the standard 16-bit ones, it creates some real challenges. It's
Mhm.
almost like trying to make a recipe where some ingredients need to be measured in teaspoons and others in tablespoons.
Mhm.
The tools aren't always designed to work with both.
Okay, so how does Google solve this problem? Do they have to, like, redesign the hardware?
That would be quite an undertaking. Fortunately, they've found workarounds using some clever software techniques.
Oh, okay. The Google AI blog post highlights two main hurdles they had to overcome.
Okay.
The first one is data type conversion.
Data type conversion sounds a bit technical. Can you break that down for us?
Sure, think of it this way. Imagine you have some data written in English and some written in Spanish. If you want to understand both, you need a translator to convert them into a common language.
So Google had to build a translator for the tensor cores.
Essentially, yes.
Hmm.
They needed a way to convert those 8-bit and 16-bit numbers into a format the hardware could understand. The article mentions that they developed a software tool to make this conversion super fast.
So data conversion handled. That's one hurdle down. What's the second one?
The second challenge, and this one's a bit more abstract, is what they call layout conformance.
Okay, you're going to have to walk me through that one. What exactly is layout conformance and why does it matter?
Okay, the best analogy is to think of a jigsaw puzzle.
Right, I like puzzles.
The hardware of those tensor cores expect the data to be arranged in a very specific way. Like the pieces of a puzzle fitting together neatly.
Yeah.
Makes sense. You can't just force any piece into any spot if you want to complete the picture.
Exactly. But sometimes the data comes in a different arrangement, like having all the edge pieces mixed in with the rest. It won't fit the way the hardware expects. So Google had to come up with a way to rearrange the data on the fly to make it conform to the layout the hardware requires. They call this technique fragment shuffler.
So it's like they have a puzzle expert who can instantly rearrange the pieces to make sure they all fit together properly.
That's a great way to think about it. And here's the amazing part. All of this conversion and rearranging happens incredibly quickly.
That's pretty impressive. But what's the bottom line here? What does all this mean for the average person?
Well, what's really exciting is that these optimizations, the data conversion and the layout changes, bring the performance of these mixed input calculations very close to what you'd get with the standard hardware-supported data types.
So it's almost like getting a free speed boost just by being clever about how you handle the data.
Exactly. It's about squeezing every bit of performance out of the existing hardware. And that has huge implications for the future of AI.
All right, I'm definitely intrigued. Let's move on to part 3, where we can discuss what all this means for the future of AI. So we've spent the last 2 parts of this deep dive really getting into the weeds of how Google is making AI faster and more efficient.
Yeah, a lot of really interesting technical stuff.
It's been a wild ride. But you know me, I always like to zoom out and look at the bigger picture. What does it all really mean? Why should our listeners care about all these behind-the-scenes optimizations?
Well, I think what's really fascinating here is that it reveals a fundamental shift in how we think about AI development. It's not just about building bigger and bigger models or using more and more powerful processors.
It's about being smarter and more resourceful with what we already have.
Exactly. It's driven by necessity.
Necessity. How so?
Well, training these massive AI models requires an incredible amount of energy, not to mention the cost of building and maintaining the supercomputers that can even handle these tasks.
Right. It's not exactly sustainable to just keep scaling up forever.
Exactly. So finding ways to do more with less to make AI more efficient, it's essential for the long-term viability of the field.
So it's not just about making AI faster. It's about making it more sustainable, more democratic, more available to researchers and smaller companies, and maybe even individuals.
That's a great point. The more efficient these models become, the less reliant they are on those massive centralized computing resources. Imagine a world where anyone with a decent computer could harness the power of AI.
That's a pretty exciting vision. And these optimizations that Google is working on, they're a big step in making that a reality.
Absolutely. And this is really just the beginning. As hardware continues to evolve, as we develop even more sophisticated algorithms, the possibilities for AI are truly boundless.
It really is mind-blowing to think about all this from just being clever with memory and data. Well, that's about all the time we have for today's deep dive. But before we wrap up, I want to turn things over to you, dear listener. What excites you most about the future of AI? Leave us a comment because we'd love to hear your thoughts.
And until next time, keep exploring, keep learning, and keep diving deep into the fascinating world of AI.